Now let's talk about another interesting sorting algorithm, which is quicksort. Quicksort is again based on divide and conquer concept and follows a recursive approach. Let's try and understand. So basically in quicksort, the crux is that at every time, or for that matter every time, what we do is that we try and have a pivot. So let's say I take 5 as pivot. Okay, so now when I take 5 as pivot, my agenda will be to divide the array into two parts. Okay, all the elements before 5 will have value less than 5, and all the elements after 5 will have value greater than 5. Okay, and now again let's say I go to the part where, before 5, where all the elements are having value less than 5. So again in that, again I will find the pivot. Again I'll do the same thing. Let's try and do this. So let's say in this case what I do is that let's say I choose 5 as pivot. So what are all the elements that is before 5 or less than 5? Okay, so it's going to be, let's say, 1. Okay, it's going to be, what else I have, 0. Okay, it's going to be 4. Okay, these three are the elements that are less than 5. And what are the elements greater than 5? It's going to be 7, it's going to be 6, 9, 8. Okay, 1 2 3 4 5 6, 1 2 3 4 5 6 7 8. Okay, now I got it. So now let's say I did some operations and I put it in this way that all the elements before 5 are less than 5 and all the elements after 5 is greater than 5. Now let's see some operations I did, and after this operation my array looks something like this. So let's say it looks like 4 0 1 5, let's take it 8 9 6 7. Okay, let's say it looks like this. So now if you see, all the elements before 5 are less than 5 and all the elements after 5 are greater than 5. So now what is happening here is that all the elements before 5 are not sorted. Keep this in mind. It won't be like all the elements before 5 will be sorted in that order. That will happen eventually, but after the first pass, what I do is that I just find all the elements less than 5. Now let's just go ahead. So now what I'll do is that I'll again choose a pivot. So let's say I choose 1 as the pivot. Now what I'll do is that in this part of the array, I will choose all the elements less than 1, and I'll choose all the elements greater than 1, and all the elements on the left are less than 1 and on the right are greater than 1. Okay, so after this operation my array looks something like this. We have 0 1 4 5 8 9 6 7. Okay, so now I see that this part of the array is already sorted. Okay, now what I'll do is that I'll go to this part of the array. So again, let's say I always choose the last element as the pivot. So again I choose this. I'll now try and find all the elements less and greater than 7. So let's say after some operations, what happens is that we have, let's say, what are the elements less than 7? It's just 6. So we will have 6, 7, 8 and 9. Okay, so here this is the pivot. All the elements less than 7 is 6, and I see that 6 is a single element. So let's say this is already sorted, and here as you can see this is sorted. If there wouldn't have been sorting, we would have continued the process. So this is what is the agenda in case of quicksort. I find a pivot, I find all the elements that's less than I find all the elements that is less than that particular pivot. All those elements will be on the left and all the elements greater will be on the right. So now after that what happens is that we have this pivot, we have less than pivot elements this side, greater this side. Now my agenda is to sort this element, this element. Again, to sort this particular part of the array, the concept remains the same. What I will do is that I will go ahead, find a pivot, find the right place for the pivot. All the elements in the left and right are like that. So as you can see, what is happening every time is that I am trying to divide the array. Now here the array will not be divided exactly into half. Like in case of merge sort, we divided the array exactly into half. But that is not going to be the case here. Because it might happen that, let's say, I take something like, let's say there's an array like 9, 8, 2, 4, and let's say there is 7. So what will happen in this case is that, okay, this is going to divide in exactly two half, I think. Let's take 10. Okay, So in this case, if I take 10, then what will happen is that all the elements will come before 10 only. Okay, then in that case, again, I'll take another pivot. So in this case of quicksort, I'm repeating, one of the major difference between merge sort and quicksort, there are lots of differences. Obviously, the concept is entirely different. But in case you're confused that what is happening, in case of merge sort, we are just dividing the array in two halves. But in case of quicksort, I have a pivot, I'm finding the place for pivot, and all the elements before that are smaller and after that are greater. In that case, you're getting confused that in insertion also have an element and I find the right place. In case of insertion sort, what happens is that all the elements before that element are already sorted, which is not the case. So now let's just go ahead and see how we do the partition. So this process of finding the pivot is called partition. So let's just go ahead and see how we do the partition and how we keep on doing this quick sort so that eventually we get a sorted array. Okay. So now let's say this is the code this is the complete code. So here we have quicksort, we have the same base value that if low is greater than equal to high, we return, we will see why is that. And then we have pivot. So first we find the pivot. So as we saw that we first found the pivot, and then after finding the pivot, we again run quicksort in this first half and in the second half. Okay, this is what we keep on doing. So let's just take an example and let's just try and see that. First we will understand this partition thing. First we will understand how do we find the right place for pivot, and for that matter how do we ensure that all the elements before pivot are less and after pivot are greater than pivot. Okay, so let's say I take this as the pivot. Okay, so it's going to be 0 1 2 3 4 5 6 7. Okay, this is my pivot. Now what happens is that I store my pivot in a particular variable. So let's say I store my pivot, let's call it pivot index. So basically pivot index will be index of this particular pivot, and anyways we are going to use this pivot value only. So pivot is the value, like here pivot index is 7 and value is 5. So pivot, let's say I store it here, it is array of high. So this is array of high because I am keeping last element as the pivot. In some code you will find first element is kept as pivot, which is absolutely fine, doesn't matter much. So now let's just go ahead. So what happens here is that there are two variables. If you see, we have I and we have j. So what is I? So basically the task of I is to keep track of the number of elements that is less than pivot. Okay, I always keeps track of the number of elements less than pivot. But now what happens is that here we know that we always place element at index -1. So let's say if I have to place element at the first place, I will place it at index 0, not the first place. This is the first place, right? So first place is represented by index 0, second place by index 1. So this is what I does. So let's say if there is one element smaller than 5. Okay, so what we will do is that we will place it at 0th index. So basically this I at every point, it keeps track that what is the right place. Okay, let's put it this way, it keeps track that what is the right place for that element which is small than pivot, and where should I put it. So that is the task of I. So I'll repeat, the task of I is that if there is any element that is smaller than pivot, I have to find out what is the right place using I. I keeps track of that. Okay, and also at the end, this I plus 1 will give me the pivot point. We will see how. Now what is j? J will start from the first place, and the task of j is to go throughout the array and find out all the elements that are less than pivot. Okay, now let's just go ahead and run this code. So initially my I is low -1, like initially I ensure there is no, I assume that there is no element less than pivot. Okay, so I keep it -1. Okay, now what happens is that I start from j equal to low. I start from here and j less than equal to high -1, basically j goes till the end. Okay, now I check that if there is any element less than pivot. If I check any element is less than pivot, what I do is that increment my I. Okay, so let's say here 1 is less than pivot, I increment my I to 0. Okay, now this particular part, it is doing nothing, it is just swapping. So at any point, what happens is that wheresoever my j is, I find that there is a place, there is a element that is smaller than pivot, I just swap it with j. Why? We will see. So here let's say my I is 0 and j is also 0. So what happens is that we swap with, this is the task of swapping the value of ith index and jth index, and since both are same, there won't be any swap. Okay, now my latest I is 0, j is also 0. After this operation, this is the end of the loop, okay? After this operation, again I increment my j. J comes here. So is 7 less than 5? No, I go here. 6 less than 5? No, I go here. So my j is incrementing. I go here means my j is incrementing. Now my j is 8. Okay, 8 is less than 5? No, I go here. 0 is less than 5? Yes, 0 is less than 5. Now what I need to do is that I need to increment my I. So I have to find the place for 0 such that 0 is at a place such that it is coming before the pivot. So now what I did was that last element that was the last element that is smaller than pivot was at index 0. So what I'll do is that I'll keep the next element at index 1. And how will I do that? I'll increment my I to 1. Okay, I increment my I to 1, and what I do is that my j is equal to 4 right now. I just swap both the elements. I know this element is greater than pivot only. I know that for sure, else my I would have been in that particular manner. So now I swap these two values. So after this particular operation, so this particular operation gets executed, my I is 1. So our array looks something like this: 6, 8, 7, 9, 4, 5. Okay, so now this is how it happens. Now let's go ahead. Okay, so now I come 7. Oh yeah, so now my j gets to 9. Again, 9 is smaller than not smaller than pivot. I go to 4. Okay, now I go to 4. Now what happens is that again 4 is smaller than pivot, so 4 should come here, right? So I'll increment my I to 2 and I'll swap these two values from this particular operation. Now it becomes 1, 0, 4, 8, 7, 9, 6, 5. So I see j goes till high minus 1. So okay, so one thing to remember here is that here high is 7. Okay, my high is 7. Okay, this is the index of the last element. So last element is, since last element is already the pivot, no point of going till here. So the iteration of j stops at this particular place only. Now what happens is that I know that all these elements are equal to 2. From 0, 1, 2, all the elements are less than pivot. So what is the right place for pivot? This is the right place for pivot. So what I do is that I simply swap these two values. This is what I do here. I simply swap. So these 3 lines and these 3 lines, they are doing the same thing, swapping. So make sure when you are writing the code, you just keep a function swap which just swaps the two values. I have kept it just to make you guys understand. Okay, so now what happens is that I swap these two values. Okay, sorry, I swap these two values, not these two. I swap these two values. Okay, now after this swap, my array looks something like this: 1, 0, 4, 5, 7, 9, 6. So as you can see, this is the pivot. So my 0, 1, 2, my I is this particular place. What I do is that I put temp equal to add I plus 1. So I just swap I plus 1 index, the value of at I plus 1 index, with the index that is at the end. And now we know that this is my pivot point. So I simply return I plus 1. So this pivot gets the value here as I plus 1, which is 3. Okay, so this is how we do the partition. Now what happens is that again we call quicksort low comma pivot minus 1, which means I call quicksort 0 to 2. After we get the pivot, we call quicksort 0 to 2. Now again what will happen is that this gets called. Again I'll try and find the partition from, I'll try and find the pivot from 0 to 2. Again these set of operations will perform, and what will happen is that eventually we will find the pivot. So for now, since we have understood how to find the pivot, now let's just go ahead and dry run just this part of the code just like we did there, and let's try and make the recursion tree and try and understand how things goes. Okay, now let's try and dry run the quicksort code. So we have already seen the partition code and we have seen that how partition happens. Okay, so what happens in case of quicksort is that we have this condition that if low is greater than high or equal to high, we return. Okay, and we have the code to the statement to find the pivot. Once we have the pivot, we will run quicksort on low comma pivot minus 1. So in the range before pivot, and we are going to run quicksort after the pivot. So that is the agenda. So let's try and dry run it. Okay, so let's say we have this 0, 1, 2, 3, 4, 5, 6, 7. Okay, so what I'll do is that first quicksort will be called, and the low will be 0 and high will be 7. Now from here we'll first check that if this is true, no. So what will happen is that first we will have the partition. So now this partition will get called, let's call it PS with value 0, 7. Okay, and this partition will return the value of pivot as, let's see, it's going to be 0, 1, 2, 3, 4, 5, 6, 7. So we got the first pivot as 3. Okay, so now this partition gives the value 3. Now what will happen is that we will call this particular statement, we will have quick sort low comma pivot minus 1. So what is low? It is 0. What is pivot minus 1? It's 2. Okay, so from here again we call this, the low becomes 0, the high becomes 2. Is this true? No. We again call partition. So now we have partition 0, 3. Okay, my bad, it's going to be 0, 2. Okay, now let's say I have to find partition here. So in this case, what is going to be my pivot? First we take this last element as the pivot point, okay, or the pivot element, and then we try and find what is the right place. So I see that this particular element is already at its right place. So what will happen is that we will get the pivot as 2 only. So this partition will give me the pivot value as 2. So now what I will do is that I will call quick sort. So now we will have quick sort low comma pivot minus 1. So which is going to be 0, 1. Okay, since pivot was 2, it's going to be 0, 1. Okay, now again from here we make a call. Okay, now again we have partition 0, 1. Okay, so now we will have 0 and 1. So here this is going to be my, what is this? This is going to be my last element. So I have to find out that what is going to be the pivot. So I have to find all the elements less than 0, greater than 0, and we will have the partition accordingly. So I see that the right place for 0 is going to be the index 0. So here this partition is going to give me the value as 0. Okay, so now after this I will have two calls, QS 0, minus 1. Okay, and I will have 0, minus 1. So now I come here, low is greater than high. Yes, this condition becomes true. So I return. So now what happens is that for the value of low as 0, high as 1, and the value of pivot as 0, what happens is that I have executed this particular statement already. Now after this gets executed, and this particular statement has got executed for low equal to 0 and pivot minus 1, we come to this particular statement, and this particular statement has to get executed. So now we call QS pivot plus 1 comma high. So what is pivot plus 1? So pivot here is 0. Okay, and what is pivot plus 1? It's going to be 1. And what is my high? It is 1. So we call QS 1 comma 1. So what happens is that QS 1 comma 1, this gives me the answer as true, right? So this becomes true and we return. So after this particular part is executed, this part of the array will look something like that. We will have 0, 1, and this particular point will be 0, 1, 4. So now after this particular complete thing is executed, we have with us 0, 1 and 4. Okay, basically rest of the array looks like this. Okay, this is how my array looks. Now what happens is that after all three gets executed, we come back here. Okay, so now this particular call that happened, all the branches of this have got executed. There is nothing remaining in here. So what will happen is that just the statement that was after this particular statement will get executed. So our statement after this particular statement was this statement for the value of pivot as 2. Here my pivot value was 2, right? And what was my low? My low was 0. What was my high? My high was 2 again. So what I'll do is that I'll call pivot plus 1 comma high. So I'm going to call QS pivot plus 1 is going to be 2 plus 1 3 comma high. What is my high going to be? High is going to be 2. Okay, so now again what will happen is that this will give me, I'll go here, it will return. So now after it returns, what will happen is that we go back. Okay, we go back to this place. Now what will happen is that whatsoever is the statement that was after this particular statement will get executed. So what was the statement just after this particular statement? It's going to be QS. My partition is 3, right? And what is my high? It's 7. So now this has got executed. I have to execute this. So it's going to be pivot plus 1, which is 4 comma high, which is 7. 4, 7. So now what will happen is that the same thing will get executed for QS 4, 7. Basically this particular array. and what will happen is that we will get this particular part of the array sorted in the similar format. So this is how quicksort works. So always what happens is that you have to keep track of the value. So many times what will happen is that the reason we are making tree is that, let's say you know it very well that after this particular state function is called, let's say this particular function is called with corresponding parameters, and let's say this particular function returns. Okay, so you know that as soon as this particular function returns, I go to the next statement. Now, but let's say at this point you're not keeping track of the value of pivot, so you will get confused. So as you can see here, I was keeping track of the value of pivot at every point, so and the value of low and high. So that was helping me in making the recursion tree. So make sure you make the recursion tree on your own, and it will make you understand things even better. Okay, now what is the time complexity? So the time complexity for this is going to be, let's first see the best case scenario. The best case scenario happens when your array is divided into exactly 2 halves at each and every stage. So in that case, it will be 2 into tn by 2 plus what will be the time complexity for finding the partition. We saw that for finding the partition we go to complete array, so it's going to be O of n, and we see that it is going to be O of n log n. Okay, so this is the best case scenario. The worst case scenario is that at every time what will happen is that partition will be such, there is one element on the right, and there are n minus element or n minus 2 elements on the left. Okay, and this is happening every time. Okay, so in that case it will look something like this. We will have t of n equal to t of n minus 2 plus n. Okay, this is how it's going to look. This will give you O of n square. So in worst case, this is going to give you O of n square. What will be the space complexity? Space complexity is going to be, okay, so what can happen is that it will actually be t of n minus 1. Okay, so why is this happening? Because let's say in this case we have 1, 2, 3, 4, 5. So in this case 5 is going to be here. Okay, this is the pivot, it's at the right place. Now I have to sort this. Okay, now this is going to be at the right place. Now I have to sort this. So my t of n is equal to t of n minus 1 plus n. Okay, so this happens in case the array is already sorted, and this is going to be O of n square. Okay, what is the space complexity? We are not using any extra space, so it's going to be constant. So that is all about quick sort.